Hi, I'm Will, and this is my Lab 3 report. In part 1 of Lab 3, we were given a model of a star orbiting a black hole of an unknown mass m, with the star being the system and the black hole being the surrounding acting on the star. Given the star's mass and velocity, we were tasked with determining the mass of the black hole. Over the course of the report, I will explain that to find the mass of the black hole, we must first separate the forces acting on the star into parallel and perpendicular forces, and then, from there, work backwards to find the mass with the force of gravity formula. Next, I will go over the important physics. The key physics principle used here is the momentum principle. I used Newton's second law to build all of my update formulas that I use to implement a model in GlowScript, and I use parallel and perpendicular forces to help find the net force of gravity. To make better use of the parallel and perpendicular forces, I split them into their component pieces shown on the slide. To do this, I changed the force into change in momentum over change in time. The final physics component needed was the force of gravity formula shown above. This formula was used to solve for the mass of the black hole once the gravitational force was determined through the perpendicular and parallel force formulas. Here's a picture of my significant changes in GlowScript. The majority of work done in GlowScript was building up from the change in velocity to change in momentum and finally parallel and perpendicular forces. From there, we could determine the net force and solve backwards using the gravity formula shown towards the bottom. We could do this because it was stated that the only force acting on the star was gravity. Now I'd like to go over the analysis. To find the mass, I took the average of my black hole readouts from GlowScript and found it was around 2.17 times 10 to the 34. Once again, this was found by using perpendicular and parallel forces to find the net force and then solve by plugging that into the force of gravity formula and solving for the missing mass. Next, I want to discuss parallel and perpendicular forces. One way to look at a net force is as change in momentum over change in time. If net force can be broken into parallel and perpendicular forces, it is only logical that the same can be done to change in momentum over change in time. By doing this, we can find the components used in the previous slide. The, the component that represents parallel force represents magnitude and points in the same direction as momentum, while the other represents perpendicular force and represents the direction. If these two change in momentum over change in time vectors were to be combined, they would be equivalent to the net force. This once again shows that net force is equivalent to change in momentum over change in time, with no matter if it's split into parallel or perpendicular forces. Part 2 was much more open-ended than Part 1. We were tasked with finding the initial velocity of a rocket that could avoid wrecking on the planet it is leaving as well as the black hole nearby. In this case, the system was the rocket ship, while the surroundings consisted of the planet and black hole, each with significant gravitational force. To tackle this problem, I mainly focused on the gravity formula as well as the escape velocity formula to choose my velocity. Once again, the gravity formula is essential to this problem as the only outside forces acting upon the rocket are the gravitational forces of the planet and the black hole. The other formula is the escape velocity formula, which can be derived from the kinetic energy formula as we did in class. This formula is essentially useful to finding out how much velocity is needed to leave the planet. It allows us to find the initial velocity needed to escape a mass of size m and radius r. Here's a picture of my GlowScript model and code. The code is pretty standard, and the model shows that the spaceship was able to escape the planet without crashing, as well as move pretty close to the black hole without being sucked in. On the GlowScript, you can see that I modeled both the position and velocity of the ship, as well as the planet. Next, I would like to discuss how I found that particular initial velocity shown at the top of the GlowScript. While determining the initial velocity for the y-axis, I chose to use the planet's escape velocity in addition to its speed. The escape velocity guaranteed that I could escape its gravitational force. However, because the planet is moving, I needed to consider that I needed to move at least faster than the planet's initial velocity, which was only moving on its y-axis. Therefore, by adding the escape velocity to the speed of the planet, I could escape the planet's gravity and avoid getting hit by the moving planet. For the x-axis, I choose to move with the escape velocity of the black hole. This is a safe option and basically guarantees that the ship could not be sucked into the black hole unless it flew directly toward it. To get the ship to orbit the black hole, which was an additional question, I changed its x velocity to 0. This means it was only moving with the y velocity I mentioned earlier, which was the addition of the planet's velocity to the planet's escape velocity. This way, it was still fully able to escape the gravity of the planet and avoid getting hit by the planet, but it was not moving with such velocity that it was able to escape the gravity of the black hole and instead entered an orbit as shown on the picture below. And finally, I just wanted to talk about one source of error that might be applicable here, and that being my measurement for the mass of the black hole might not be a perfect match. Because the mass was taken at many different points, each slightly different from each other, and I ended up taking the average to come up with the result of my mass, there might be some deviation between the average mass and the actual mass, but I figured that would be the best course of action. Thank you.